Uh, so I was saying to the group at lunch, I often will evaluate workshops or conferences that I go to based on the number of people when I look out into the crowd, the number of faces I recognize, and use that to judge, is this community growing or resting in place or somewhere in between. So on that, I am really happy to introduce our keynote speaker and introduce our MMA sessions. We'll have one this afternoon and one tomorrow morning. And for me, the exciting thing about that is I don't know any of these people, which for me is great opportunity. I'm looking forward to some great discussions and to really learn about the MMA community and hopefully at some point identify some overlaps. Now, because of all this, it means that I had to actually, for once, write down the introduction. And so if you'll excuse me for reading, we're going to really flatter you, Michael. So our keynote today is Michael Coughlin, who's an associate professor of physics and astronomy at the University of Minnesota, where he leads the data science group for multi-messenger astronomy or multi-messenger astrophysics. So I'm told Michael's one of the most ambitious young scientists in the gravitational wave community, and there's hardly a corner of LIGO or IGWIN low latency work that he has not been actively involved with. He's part of the team behind the first Kilonova counterpart of a LIGO detection in 2017. He co-chairs the LIGO Virga Cagra working group that runs the low latency alert operations. And he has been instrumental to organizing the community's thinking about the long-term architecture of the gravitational wave alert system while building tools for it himself. So getting an alert from a gravitational wave detector to telescopes around the world within minutes, sometimes even before the merger itself, is very much an HTC problem. So we're very happy to have Michael here because he works at every layer of it from top to bottom. And Michael, if you pay me enough, I'll tell you who I had ghostwrite that introduction. So his talk today is the present and future of multi-messenger astrophysics. Please join me in welcoming Michael.
All right, that was way too kind. Hi, folks. It's wonderful to be here. Thank you to the organizers for inviting me. I also don't know too many faces in the crowd, so it's been really, really nice to chat with folks. My name's Michael. As mentioned, I work on a number of astronomical experiments, mostly at their interfaces, and there are many ways in which we're interacting with computing, in particular HTC computing. And so I'm going to attempt to introduce kind of multi-messenger astrophysics and my own very biased view on some of the computing problems that we face. But the reality is that the talks that are going to follow mine with the graduate students that are actually doing the work, right? So so please listen to this talk with that in mind. Oh, it's fine. I'm just going to click forward this way, I think. It's not clicked in. That's okay. Boop. Or like this. Nice. That'll work. Okay, so I usually give this slide to physicists to explain to them why astronomy matters. Here I am to computer scientists to also explain why astronomy matters. We're in a golden era for astrophysics. There are many, many different instruments that are coming online now, have been running for decades in the case of LIGO, Virgo, and Cagra. Coming up in the future, Rubin Observatory, which was already mentioned when Maron was talking at the very beginning. It's a really, really exciting time to be working in astrophysics. And so one thing I'm going to be talking about today is not only how these instruments work individually, right? And so they of course have all of their own science cases, and there's many things that you can do with them completely on their own. But the promise of multi-messenger astrophysics is how we can use them together. And so we'll be talking about that. And so to sort of set the stage here, I am a so-called gravitational wave astronomer. And so to explain what that means, we have to start with Einstein. Um, and so Einstein had his famous theory of general relativity. And the very famous quote in our community from John Wheeler, which tries to kind of explain GR, matter tells space-time how to curve, space-time tells matter how to move. And so the observables that we're going to be talking about in the talk today are literally us studying space-time. And so so space-time itself is permeated with this with these waves that we call gravitational waves. And so gravitational waves are perturbations in this space-time that are caused by high energy astrophysical phenomena, things like black holes and neutron stars. And it's actually been many, many, many decades that we've known that these gravitational waves exist. And so I've actually met a couple of Carleton grads in the audience, so I just want to mention this briefly. I learned astronomy back at Carleton College from a man named Joel Weisberg. And Joel was a postdoc back at Princeton many, many years ago. And what they were doing is they were studying the spin period of what's known as a binary pulsar system. And so a pulsar is a neutron star, which is this very dense star made of neutrons. And what happens is that as these two neutron stars orbit around one another, they're emitting energy in the form of gravitational waves. They're losing energy into space-time. And you can actually track that loss in energy by measuring the change in period over decades. And so if you look at the plot on the right-hand side here, on the y-axis, you have this change in period, and then on the x-axis, you have years. And so you'll notice that this plot spans decades, and you'll see all of these red dots that correspond to these measured periods. And overlaid in this black line, and I'll emphasize, this is not a fit, right? This is a prediction by Einstein back in the early 1900s of what the expectation of this energy loss was, and it matches perfectly, right? And so Joel's advisors actually won the Nobel Prize for this discovery back in 1993. But it's this, there's many things that are really exciting about multi-messenger astrophysics to me, but this confrontation between data and theory is really incredible in the areas in which we work. And so how does sort of gravitational waves behave? So gravitational waves produce what are called strain, and I'll see if I can play this a second time here. There we go. Okay, so what's happening is as gravitational waves permeate through space-time, they're expanding space-time in one direction and contracting it in another direction. And so you kind of saw it in this little image here where as gravitational waves are moving this way, space expands this way, contracts another way, and then it'll expand this way and contract another way, right? And so space is actually expanding and contracting, again, due to these high energy phenomena. And here's a nice little GIF where you can, try to visualize that as well. And so you may be thinking to yourself, how the hell do you guys actually go try to observe these, right? And so if for some of you, maybe you took a physics class back in college, and you might have been introduced to this idea of interferometers. And so the way an interferometer works, and we'll sort of watch this animation together. But the idea is I have a beam of light that goes out to a beam splitter, goes to mirrors at the end, and then bounces back. And so we'll walk through this. So light's coming out of this laser, hits a beam splitter, goes to the very end of one of these mirrors, hits the mirrors, and bounces back. And depending on the distance between these two mirrors, I will get constructive or deconstructive interference out on the photodiode at the end. And so this is a concept that's been known for more than a century, how interferometers work. And so what's actually really incredible about these gravitational wave detectors is that they're actually built on relatively simple technology. And so what's happening here is that as the gravitational waves expand space in one direction, contract another, I will get signal out on this photodiode. Okay, so back in junior lab, back when I was a physicist, we built a little interferometer. Maybe the mirrors were a foot apart or something like this. I had a little laser sitting on the desk. What LIGO does is it takes this this experiment, to kind of its natural conclusion at some level, right? So we build these 4-kilometer detectors. There are 2 in the United States. One is in Hanford, Washington. One is in Livingston, Louisiana. And here's a little movie showing the sort of what the beam tubes look like and what the instrument looks like inside. And while indeed there's, let's say, advancements on top of kind of the relatively simple Michelson interferometer that I explained, the reality is it's really fundamentally an interferometer. And so we do play many games in order to, for example, increase the number of photons that we can have in the arms of our beam. For example, we do something called signal recycling, where actually we build up photons in the beam to increase its laser power something like 100 times or so. The idea being that the more photons I have in my interferometer, you can think of each of those photons as their own individual detector. And so the more photons I have, the more capable my interferometer is of, in this case, detecting gravitational waves. And so we have a worldwide network of these gravitational wave detectors. As I mentioned, there's 2 in the US, one in Hanford, Washington, one in Livingston, Louisiana. There are a couple in Europe. One is known as GEO, which is just outside Hanover, Germany. One is known as Virgo, which is outside of Pisa. Kagra is a Japanese detector actually built in a mine. And then there's a third so-called LIGO detector that's being constructed in India. Just a really brief story about that. Back when I was an undergraduate, again at Carleton College, we were in the midst of what was known as Science Run 5. And so the graduate students, the astronomer graduate students in the audience will be like, you don't name your runs that way. This is how old I am, right? We've actually changed the names of how we do our runs back then. And what made those detectors different, or at least one thing that made those detectors different, the LIGO Hanford experiment was not one interferometer, it was 2 interferometers in the same beam tube. And so while that might not seem like a big deal, one must imagine that these experiments, they're subject to earthquakes, magnetic fields, all sorts of transients that are due to environmental effects. And so having 2 gravitational wave detectors in the same beam tube, trying to make detections with them both, was not a good idea. However, we didn't realize that before that the next generation of gravitational wave detector experiments were built. And so actually there was a copy made of all of the optics and the seismometers and everything that goes into these detectors. And it's that copy that's going to India. And it's broken ground, and we'll be expecting to have a third LIGO detector around 2030 or so. And so we'll get beyond kind of the detection problem. So there's a few reasons why this international network is important. The first one is for detection purposes. It's actually really hard to measure gravitational waves with a single detector due to the fact that there's so much that goes on, so many noise sources that goes on. And so we really like having a network to be able to tell us, this gravitational wave is astrophysical, it's not made by humans. But the second is related to localization, which we'll just get to in a second. But before we get there, I just want to have us visualize just the kind of astrophysics that we do here. And so what I'm going to play for you here is a little movie where we simulate the merger of 2 black holes in this case. So we're only starting, you'll see in the top left-hand corner, 0.7 seconds before these 2 black holes merge. And then on the bottom of the screen here, as I have my gravitational waveform. And so what you have is these two black holes. They are getting closer and closer together due to the emission of gravitational waves. They are losing energy due to um, emission into space-time. What I have in the gravitational waves here, I have this sinusoidal signal as they are, before merger, approximately monochromatic, basically. However, as they get closer and closer together and come closer to merge, the period of their orbit is getting shorter and shorter, and therefore the frequency of their gravitational waves is getting higher and higher. And so what I'm going to see here is I'm going to have this characteristic, the so-called chirp signal, where these two black holes are going to merge. We call it a chirp because actually it's in the audio band. It sounds like a whoop, right, as these two merge. So we have these black holes that are merging. And then this final black hole is emitting gravitational waves. It's like ringing like a bell as it loses energy. And so this is what the signals that we look for in our data look like and how they correspond to the real astrophysics. And so just to give you a sense of what this looks like when you include noise, and so you can hear this nice chirp. The way that we'll often present data, and it's useful not only kind of for the aesthetics, right? So if we compute spectrograms, and so what's happening here is I've taken my time series of my gravitational waves, I've taken a series of Fourier transforms, and I put them all together, and so you can see here this really nice chirp signal. And it's very common for these gravitational wave search algorithms to use a variety of modalities. Some use time series directly, some take Fourier transforms. Often they will produce spectrograms. And so beyond just the fact that our gravitational wave detectors, we have multiple gravitational wave detectors and therefore multiple streams, our data is often also represented in multimodal fashion, which when we'll get to in a second, lends itself to a lot of the developments in machine learning. Okay, and so while that's all well and good, right? I have two black holes that merge. What kind of astrophysics can I do with this? And so the way this little GIF is going to work. So in blue here, I'm going to have some simulated data, and then in orange, I'm going to have predictions of what those gravitation waves should look like, depending on the distance to this binary black hole system and the mass of those binary black holes. And so what we're going to see as this plays, an algorithm will sweep through both total mass and distance to identify the correct parameters for these binary black holes. And for some of you, this might not seem like a big deal, right? Like, okay, so you can measure how large these things are, you can measure how far away things are. In astronomy, measuring distances is very, very hard, right? There's no rulers that you go out and you measure the distance between these two stars. Often measuring distances in astronomy is very subject to assumptions and systematics. And it really matters because when I'm trying to measure how fast the acceleration of the universe is expanding, for example, distance is everything. And so what makes gravitational waves exceptional is that if I believe Einstein, I believe in GR, which we often also test, right? Some of you in the audience actually work on this. But if you believe Einstein, you get an estimate for distance that is with systematics completely unlike exists for sure, in optical astronomy. And so gravitational waves are just really exceptional measurement tools for this reason. Okay, and so we've been detecting gravitational waves since 2015. I started in LIGO in 2008. Some of the folks in the audience have been doing LIGO for longer than I have. But the reason I bring this up is gravitational wave astronomy is actually a very young field, at least in terms of time domain interferometer detections. It's just in the last decade that this field has really been blooming. There was a Nobel Prize given to Ray Weiss, Kip Thorne, and Barry Barish a number of years ago. Unfortunately, Ray passed recently, but uh, it's actually just been, again, not very long that we've been really doing this. And despite that, we've really changed the way one studies compact objects in astronomy. And so this is an image shown from a data release that just came out last week. So our fifth gravitational wave catalog just came out. So the way this plot works is in the orange here we have neutron stars. In the blue we have black holes, and so every blue dot here corresponds to a black hole we've discovered in gravitational waves. For comparison, the yellow and the red here are neutron stars and black holes that we've discovered in electromagnetic and photons. And so we do know about some of them from things like X-ray binaries and other ways, but we've really exploded the field in terms of studying these objects. Now, we're going to talk a little bit about many of our favorite gravitational waves. And so this is what's known as a binary neutron star merger. And so for those with astute eyes, you'll remember that when we were looking at the gravitational waves from the binary black hole, we were just showing about 1 second of data. You'll notice here we're covering something like 30 seconds. Gravitational wave, the amount of time a gravitational wave is present, or kind of this chirp, is inversely proportional to how large they are. And so what this means is that the phenomena that we're looking at here are not as large as black holes. They're actually much smaller, these things known as neutron stars. And so this is really exciting for an optical astronomer, right? So we've been talking a lot about gravitational waves, but we haven't been talking much about electromagnetic astronomy, but this is where we start talking about it. And so what's really exciting is, well, for binary black hole mergers, one doesn't really expect a lot of photons, right? One can construct reasons that might be the case, but for neutron star mergers, we know they produce photons. And so this brings us to the idea that we want to do electromagnetic follow-up of these gravitational waves using telescopes. And so the unfortunate reality of gravitational wave detectors, they're really, really cool, but they're really like radio antennae where they don't tell you exactly where to look. And so we need multiple detectors and using time delays to try to measure where they are in the sky. And so what this sky map shows is we have these bananas, for those of you who've seen our localizations before, but these green bananas correspond to what our gravitational wave network knows about where the gravitational waves are. And so we'll play a little GIF here. So this is an example from 2017 where we detected gamma rays, so Fermi and Integral are gamma ray monitors. And then LIGO, let's see if I can click through this. Oh, it's playing. No, that's great. Okay, so then from the gravitational waves, so these is these LIGO bananas that we had. And when you included our third detector, Virgo, our European partners, they localized it to something like 40 square degrees on the sky. In only 40 square degrees, there's a limited number of galaxies that we'd expect to host these neutron star mergers. And by looking through that set of galaxies, you were able to actually identify and pinpoint where was this neutron star merger that appeared. And so back in 2017, we discovered the first counterpart. A number of teams did this to the first binary neutron star merger discovered by LIGO. You have the little blue dot there in the upper left-hand side, and over just the course of a couple of days, it became very, very red. And so another way to view this data, this is a series of spectra. So on the y-axis here, I have brightness. On the x-axis, I have wavelength. And so I'm going to play this little movie, which shows, I might have to click through. Yes, okay, so where we have this really bright blue object that faded quickly and produced features in the near infrared. This was unlike anything pretty much anything we'd seen before. And I'm going to talk, because I want to talk about some of the challenges we have, but we'll just go through the physics here a little bit. Kind of, compact binary coalescences 101, let's say. There are many physical phenomena producing photons when two neutron stars merge. And so the first phenomena are known as gamma ray bursts, where I have material that I have the formation of a jet that interacts with the surrounding material and produces high energy photons, these gamma rays, which we detected within around a second of the gravitational wave. So here's that gravitational wave spectrogram, and less than a second later, the gamma rays appeared. Then the material from as the material cascades out into the surrounding environment, into the interstellar medium, you get interactions which produces the panchromatic afterglow, which you can see all the way from radio waves all the way to X-rays, through the optical everything. And so we've actually been detecting these for a few decades now. But the particular phenomena that we're really excited about is known as a kilonova. And so to explain these, we'll have to talk a little nuclear physics here. And so one of the kind of the founders of kind of time domain theory is a guy named Brian Metzger at Columbia, and he's this quote to explain what's going on. Kilonovae are electromagnetic counterparts of compact object mergers powered by the radioactive decay of our process nuclei. Okay, what does that mean, right? So I have some kind of seed nucleus with protons and neutrons, and I'm in this midst of this neutron star merger where I am in a very neutron-rich environment. And so there's a process known as the R process where these neutrons can be captured by these seed nuclei, and you form these very heavy elements. They're very unstable. If I have unstable elements, they're going to undergo radioactive decay, and they're going to produce gamma rays. And so it's these gamma rays that then interact with this hot soup of neutrons that heat it up, right? So we say thermalize, and as these gamma rays thermalize that material and it cools down, well, it just turns out that the temperatures for that thermalization is something like 10,000 Kelvin, which turns out to be right in the optical, right? And so we can actually see the formation of these heavy elements and the radioactive decay by actually pointing optical telescopes at these neutron star mergers. And the fact that this all just sort of works out, it has a bunch of implications for physics. For example, studying the neutron star equation of state, neutron stars are one of the only ways to study hyperdense atomic physics or nuclear physics. Shooting atoms together, something like Frib or something like this, you can get to maybe 1-ish times nuclear saturation density, maybe a couple. Neutron stars are the only ways to really study nuclear physics in truly dense environments. And so we use neutron stars to actually try to understand nuclear physics. We can also do cosmology. So as I mentioned, there's this huge crisis in physics trying to understand why is the universe expansion accelerating. And it turns out that a couple of the techniques that physicists use, either studying the cosmic microwave background or using type 1a supernovae, they disagree at much more than a 5 sigma level now. And like Nobel Prize winners will swear up and down that their experiment has no systematics, whatever. And so people are very interested in understanding if this is a real phenomenon or is this new physics. Well, as I mentioned towards the start of the talk, gravitational waves are really excellent for measuring distances and therefore doing cosmology. And so if we can measure enough gravitational waves, we too can weigh in on the great debate of the day. If you don't care about any of that, maybe you really love the periodic table. Merging neutron stars are either the only or at least one of the dominant ways in which we produce heavy elements. Like back in 2017, when we were trying to really publicize this, we talked about the golden event, right? Production of gold. But the reality is that the production of these R process elements, neutron star mergers, is really where it occurs. And so we're very interested in studying, abundances and everything else. And again, we have to do this to, these neutron star mergers must be discovered to do this science. And so this really leaves the question of, what will it take to find more? And so here we get to the challenges. Okay, so for the non-astronomers in the crowd, on the y-axis here, I have magnitude, and so it's this really terrible unit. It's logarithmic. As it gets more negative, the source gets brighter, and so it's just this crazy unit. On x-axis here, I have time. In black here, I have a bunch of supernovae. We will hear talks on supernovae, so we'll not talk too much about those. But these supernovae are either due to interactions of white dwarfs or sometimes in the core collapse of large stars. And these signals, they last weeks to months. They're relatively bright. Here I have my neutron star merger, 172817 here. It does not look like supernovae. It is both subluminous, it is much, much less luminous than supernovae, and it fades much, much faster, right? And so one of the words that are going to come up, I'm sure, in the talks that follow are time domain astrophysics. What I mean when I say time domain or transient astrophysics, something appears and then something disappears. Neutron star mergers are one of the epitomes of time domain astrophysics. And that's a dangerous statement with some of the people in this crowd, but it's one of the most challenging sort of observational problems in astronomy today. Okay, so finding kilonovae are hard. The other reality is that there aren't that many neutron star mergers to find in the first place. And so these are estimates from our most recent observing runs. So the only column that we'll pay attention to just for the moment is this one here. So this is the expectations based on our current neutron star merger rate for how many neutron star mergers we should have found in the last observing run we did. I'll give you a hint, we found none. So that's not so good. And then even in future detectors where we've improved them, and we'll talk a little bit about detector timelines, but these numbers stay pretty small, right? On the order of, maybe 5 a year. I think even some of these are a bit optimistic. And so the phenomena that we're talking about is inherently rare, right? Which requires us to be very ready when they do come. This plot's very complicated, so I won't talk too much about it, but just to give you a sense, the way it works is on the y-axis, I have distance. On the x-axis, I have real time. In green here, I have all the binary black hole mergers we've discovered, which you can see here. In red is the neutron star black holes, and the blue is the binary neutron stars. You'll notice there's just not a lot of blue on this plot. The one blue circle that stands out is 172817, where I've added 6 years to it, right? And so these events that we care about are very, very rare. Okay, and so where do things stand now? So I, amongst others in the crowd, work on this experiment called ZTF, this Wiki Transient Facility, which is a camera on the Palomar 1.2 meter. Here's its little filter arm here that's putting the filter in and out of the beam. And it's a so-called survey of the night sky. We're going to be hearing plenty about these in coming talks. And already ZTF is this massive data problem. And so the way these surveys work is they take repeated images over the part of the sky that's observable to them. I'm sure we're going to see even more beautiful plots when we talk about Rubin here in a few talks. But the idea is that you take repeated observations in some sort of cadence over the sky, which sets the timescales for which you can discover transients. And so with ZTF, we've discovered many, many supernovae. We'll hear about that as well. And so in what's happening here in real time, this is the identification of white dwarf supernovae or core collapse supernovae or so-called superluminous supernovae. And what's awesome is over just the last, since 2018, we've discovered and classified more than 10,000 of these. And so this has been done over the last handful of years, kind of where are we headed. So in terms of LIGO, Virgo, and Kagra, due to funding, we are planning for a run that will start at the end of the calendar year, November, December-ish, and run for something like 6 months. The expectation is that the sensitivity should be similar to what we had during 2004. And the hope is at some point when that run is done, we will shut down, upgrade the detectors, and increase the sensitivities thereafter. All of this, of course, depends on the National Science Foundation, but this is where things stand now. On the optical side, we'll hear from Colin and others on Rubin, which is ZTF is a 1.2 meter, Rubin is an 8-meter class telescope, right? And so the sensitivity, the change in sensitivity here, it's like a paradigm shift in terms of changes in depth. It also has wider filter range. We only observe in 3 filters in ZTF. There are 6 for Rubin. Rubin is a wonderful experiment that will have big impact in multi-messenger astrophysics as it gets going here, but there are others who will talk about this. I'll also just briefly mention Argus. So Argus is a Schmidt Observatory's experiment. It's an array of more than 1,000 small aperture telescopes. It's an experiment led out of University of North Carolina. ZTF has a 50 square degree field of view. Rubin has around a 10 square degree field of view. Argus, 8,000. Right, and so it really is a game changer in terms of the gravitational wave localizations. Many of our localizations cover thousands of square degrees. ZTF already has a big challenge. May not be so hard for Argus. And so the expectation is that Argus should see first light sometime next year. And so this is, this is a big deal. Okay, but, getting with these amazing instruments, we have challenges. The data rates here are absolutely phenomenal, right? And so whether we're talking about Rubin, 20 terabytes a day, 10 petabytes per year, Roman, 20 terabytes, 7 petabytes per year. If I'm moving into the radio, the numbers are crazy. The data rates are absolutely insane, right? And so this brings up the idea that, data science must be playing a role here. And of course, with these high data rates, and we're able to use machine learning to, speed up analyses or, make analyses that were never possible before. That's all well and good, but as a astronomer who has undergrads and graduate students knocking on his door all the time asking for research projects, these days it's really the cool thing to do, right? I want to do some machine learning, I want to do some astronomy, but there's a lot of challenges, right? Actually, maintaining the GPU libraries, versioning, Hugging Face, everything else, right? These are not the things that folks are that excited about doing, and so point number 1 that I'm going to make is that when we talk about facilitating our students and postdocs doing analysis, we would like to find ways to minimize this so that people can spend more time doing the science. And so there's a collaboration built out of the NSF funded 5 years ago out of the Harnessing the Data Revolution call, a number of these AI institutes. Benedict Rydell, who's here, was one of the co-Is. I was leading the multi-messenger part of this. And the idea was to bring together domain scientists, computer scientists, and hardware engineers to bring machine learning to the sciences. And in particular, I'm going to give a couple of examples from our own field. And so the first is from gravitational waves. ML4GW is a series of PyTorch libraries that we built that enable things like data cleaning, anomaly detection, detection of compact binaries, parameter estimation, which is all wonderful. But the challenge here is that there is a massive compute problem. Now, whether I'm thinking about detection or I'm thinking about measuring false alarm rates or doing simulation campaigns, as folks in the audience know, you have to do it and it ain't cheap, right? And so the great thing about this was that using machine learning did speed up our searches, right? And so I'm pretty proud of this actually. There was when it came online, the compact binary coalescence pipeline my graduate students built, it detected this one particular event 5 seconds before any other pipeline. Now, seconds may not seem like a big deal. However, running the low latency alert system, our requirement, which we don't meet, is to send alerts to the community from data taking to alert in 10 seconds. We don't quite meet that. We are mid-20s right now. But given that, 5 seconds is actually a big deal, right? And so we are really pushing, we're using machine learning to try to push those numbers down. And the good thing about this is that we can, of course, use GPUs to try to make everything faster. And things like Triton servers allow things to scale well. But of course, getting access to GPUs within our community, it's a very contentious process these days. And so LIGO, most of our compute is still mostly done on dedicated hardware. I was just actually told by our introducer that my graduate student is the only one he can find with a NAIR allocation, which I found almost horrifying in LIGO. And so it's actually very rare still for us to be taking advantage of these resources. The challenge that we have is that a lot of what we do is latency critical, right? As I mentioned, we're really focused on putting out alerts within seconds. Right, and so some aspects of our workflows really do require dedicated resources. However, there are things like training these machine learning algorithms, applying these simulation campaigns, all of which we are starting to take advantage of and plan to for IR1 for sure in order to meet the needs. Okay, so this is kind of where things live in gravitational wave land. I'll also just sort of briefly mention the multi-messenger aspects. This is my own very biased view of multi-messenger astronomy. And so if you ask any sort of astronomer, they'll make a different plot here, but this is the one I like to show. The way I think about it is there's a bunch of optical surveys. As I mentioned, we have ZTF, we'll hear about Rubin. We also have all these multi-messenger instruments, whether I'm doing LIGO and Virgo with gravitational waves or IceCube, my neutrino detectors. And these multi-messenger instruments put out alerts to Kafka brokers. One is the General Coordinates Network hosted by Goddard. And then, so it's a NASA facility. And then CIMA is a UIUC-led effort, kind of the NSF side of this. And so everyone gets access to these multi-messenger alerts through these brokers. In optical land, people build alert brokers. I think we'll mention them in a second, but basically these are the clearinghouses that folks use to, for example, get alerts from Rubin. You have these brokers, and then finally they find their way to Marshalls, where these data are combined together. And so astronomy, in these optical surveys, yes, it's an astronomy problem, but first it's a big data problem. Rubin's producing something like 20 million alerts per night. What you have is the blue, and any given astronomer only cares about the red. But different astronomers care about different things, right? So if I'm cared about TDEs or supernovae or some kind of stars, right? Everyone cares about a different slice of this 20 million alert thing. Latency really matters. We were just talking about objects that fade really quickly. They're intrinsically rare and so on. And so we built this broker that we call Boom. We decided to write it in Rust and use Kafka and everything else. We can talk about the technical details at some point. There are 6 other sort of approved community brokers that are out there. But I'll just talk about a couple of lessons that I've taken, at least, from doing this. Years ago, and we've repeated it a couple times, simulation campaigns to prepare Rubin, to prepare expectations for what Rubin alerts like, have been made. And so these are called plastic and elastic. They have long real names that I can't remember. But what came out of them is a bunch of machine learning classification workflows that, yeah, people wrote papers. It was great. I'm sure I can actually track it down. I think like maybe 2 of these ended up in production, maybe. And what we've been doing within Boom, at least, is we've been settling on formats, things like the Open Neural Network Exchange, to try to do 2 things. One, put up technical kind of, I'm going to call it guardrails for machine learning models that we'd accept. However, if you're able to export your models into a particular format, we would at least consider running them. right? And so this is actually a very different way than other groups have done this. There, as I mentioned, there are other brokers. Some have said, we're not taking anything from the community. Others have tried to take everything from the community and failed, right? Because, trying to run everyone's, whatever version of Torch, TensorFlow, whatever it is a complete disaster. And so, we're trying to put up guardrails by putting things out in a specific format. The other thing I've learned from doing this for years, and this is true in gravitational waves, and even more so in the optical time domain, building out web apps and front ends is critical for our scientific software workflows. Yes, you can get some astronomers to understand what an API is. Most of them won't, right? And so, yes, with the introduction of Claude and Codex and so on, maybe this is going to change in time, but I've still found that, front-end development is king. But doing things like being able to have astronomers have some front-end interface to build their filters. We've started to build in, large language model tooling so they can write in, give me a Mongo query that will, give me all the supernovae and Rubin, things like this, and so just finding ways to meet astronomers where they're at. And I'm really proud to say this has really been producing some cool workflows. Back when I was a postdoc, so I arrived at Caltech in 2018 when ZTF started. For many years, the way that the Bright Transient Survey worked, the one where we found 10,000 supernovae and so on, you'd be up in the middle of the night, you'd be looking at the data that'd be coming out, and you'd be like, okay, that looks interesting, I'll go get a spectrum. Okay, then you go get the spectrum. Up in the morning, you reduce the data. You're like, yes, this is a type 1a supernova. We don't do any of that anymore. We have replaced this with robots, right? And so and it's only been for a couple of years where everything from the data taking all the way to the public release of the spectroscopic classification, all done automatically, right? And so the hope here is that we're saving graduate students and postdocs from all of that time just looking at data. Instead, they can actually care about what is the science case that I actually want to deliver here. I also mentioned that multimodality is key in gravitational waves. Of course, it's even more true, I'd say, in the optical. From the images that we take to the reduced photometry to the spectroscopy to some of these other multi-messengers, multimodal classification, is the key here. Peter asked us to think of, talk about, what are the challenges, where do we need the community? There's a lot of things I'm worried about, cost-effective inference at kind of the 10 million per night scale. How do you manage these 24/7 low latency services? Astronomers hate when stuff goes down, right? But it can be important, right? Because as I mentioned, while we've discovered 10,000 supernovae, we have 1, maybe 2 kilonova, depending on how much you believe, right? So we need services that are ready to respond over years with very little downtime. And I'll just kind of say, where I'd love to see the future graduate students headed. A lot of the messengers, despite sort of working in this coordinated software ecosystem more and more, we still don't have a lot of truly joint data analysis inference pipelines, and I'd really love to see that. Okay, so I think I'm out of time at this point, but I'll just mention, just like there have been electromagnetic wave windows, whether we're talking about the X-ray, the optical, the radio, this is also true in gravitational wave land, depending on the part of the frequency band you care about. One cool experiment that we expect is coming here in the next few years is known as LISA. So LISA is this instead of having the L detector, you put a triangle detector in space, but instead of those arms being 4 kilometers apart, they're 20 million kilometers apart. And so you can look at a completely different band of gravitational waves. And what's exceptional about LISA, right now, LIGO is Earth noise dominated, right? LISA will literally be gravitational wave dominated. We will see every single white dwarf binary in our galaxy using LISA. It's actually a huge data analysis problem. It's like, it's an awesome data analysis problem, but LISA is just going to be this exceptional instrument. There's also pulsar timing. Yeah, so I'll just sort of move through here. As I said, we got to bring this to an end. You know, I think this is a really exciting time to be working on gravitational waves. As I mentioned, we just started. We've only been directly detecting them for the last 10 years. We've only been detecting them indirectly for the last, 30, 40 years, things, like it's a really young field. If you want to get involved, we make tutorials and a lot of data available through the Open Science Center. We help run a gravitational wave follow-up program targeting amateur astronomers called Kilonova Catcher. The idea here is that we help coordinate the follow-up if you have a telescope in your backyard or wherever that you can participate. And with that, I think I'll just end here and say thank you very much.
All right, we do have time. So questions for our speaker. Frank, go ahead.
Can you go to the slide where you had the most recent catalog? This one, yep, that one. And explain a little bit the shape of this and why it's not filled in more in other directions. So for example, why do you have, is the fact that you don't have solar masses outside of a very narrow band when everything's said and done, simply a characteristics of the instrument, or what's going on?
Okay, so I should put this back here, otherwise it'll be too loud. Okay, so it's both. Okay, so the gravitational wave detectors, we take data at 16 kilohertz, so it means we're sensitive to gravitational waves up to 8 kilohertz. However, if I have on the low end, we have due to seismic noise, basically, we don't see below, 15 hertz or so, something like this. So on the low end, these very, very massive, on the high end, these very, very massive binary black holes are merging at some point kind of in this, kind of 50 hertz-ish range, right? And so we just stop being sensitive. We just don't go low enough in frequency at some point to measure larger black holes. You need something like LISA, which goes to lower frequency. Okay, so that's at the very top. That's why we don't see stuff higher. Now, on the lower end, this gap between the black holes that we have and the neutron stars. Okay, so some of this is astrophysics, right? So the thinking is that it's not that easy to make things between like 3 and 5 solar masses, right? And so neutron stars, depending on the equation of state, you can probably make them up to maybe 2.5 solar masses. People debate on how big a neutron star you can have, but kind of the quintessential mass there is something like 1.4 solar masses. And so actually making stuff astrophysically in here is hard. Now, the reason that this isn't more filled in, though, is once again sensitivity. So I mentioned that the coalescence time goes inversely proportional to total mass. However, the gravitational wave amplitudes rise very quickly with mass. And so like these 200 solar mass binary black holes, very loud gravitational waves. Relative to our neutron star mergers here, actually very intrinsically dim gravitational waves. And so astrophysically, these are, despite being in band for longer, they're actually just harder to see due to their low amplitude. So it's a mix of astrophysics and our detectors that forms this shape.
I used to work on Lego back in 2011 before, but you pointed out the slide towards the end about end-to-end. I'm assuming end-to-end in that context means from alert to processing it through the entire pipeline. If I'm a theorist or an outsider with my own sort of model, and this model is exported in Onyx, what does that look like? Do I ask you to load it in,
Hmm.
and you run it for me, or do I provide the model, but then say, here's my university computing cluster schedule jobs there. What is the actual?
Yes. Okay. So a couple of parts to this question. So the LIGO data is proprietary for something like a year after data taking. And so if one wants to if one actually wants to run a low latency search in LIGO using a model that, for example, we do not, then you have to come to us. However, if you have your own model and you're happy to use open data, we have tutorials that with AMPLFI, for example, where we show you how to download data from the Open Science Center to train a little neural network to do some classifier for your model and actually be able to run through that workflow. This is part of, again, kind of the narrow resources stuff. This is what that proposal partially kind of fulfills. So it kind of depends on what your use case is, I guess.
Right, but you couldn't inject that into the actual real-time pipeline.
Right. And so if one wants to run a real-time pipeline, one must work with LIGO people. I should say LIGO Virgo Cagro folks. Yes.
There was a question over here.
We've got an online question. How would you recommend people from a background that is traditionally computer science join these efforts of accelerating physics and astronomy by working alongside them in their data analysis problems?
This is a really good question. So a few things. Almost everything we do exists in open source repositories, right? AMPLFI is an open source repository. All of these optical alert pipeline stuff that we talk about, open source repositories. We work collaboratively with folks around the world to do them. So while indeed some of the, let's say, deployment, which we just talked about, can be physics specific, kind of collaboration rules and so on, the vast majority of the software effort is open. And so participating in those projects is very appreciated.
And then Brian had a question, and then back to Frank.
So looking at Boom versus looking at just the brokers, it seems that the brokers are kind of a watering hole that everybody can go there, listen for something interesting, go back to their own infrastructure, decide what to do. It looked like Boom was starting to think about what's almost a common infrastructure. What can we do together? Is that the right reading? Is the vision of that to start saying, instead of just a common watering hole, a place in the middle where we meet, that some of these different projects can actually have more overlap in what they do on the cyber infrastructure side?
Yes, I should say, Boom is not completely unique here. The brokers in particular have a wide variety of models. Within Boom, we are advocating for a particular vision for that, basically setting standards for if, my data will be pre-processed in this particular way, it will be able to be export in terms of particular formats. And if so, then, we will work with you to potentially run it, right? And so I think the challenge that all these brokering systems have to figure out is kind of a mix of, as we know, the compute is a challenge, but also the software support is a challenge, and how to appropriately balance that with community need is the challenge.
Yeah.
So how do we go from here? I can see opportunities for, let's say, throughput computing technologies, not for the low latency execution, but I can see opportunities. How do we bring the capacity that you need to do the low latency and deal with the GPUs falling out of the sky or turning into black holes or whatever you want to call it? So how do we go from here to have a discussion? Because I definitely see an opportunity for doing testing and evaluation of any of these hocus pocuses that you have then to run for production.
Yep.
or for reprocessing of all data. Because when you're doing a survey, I will not be surprised that you have oops moments.
Yep.
Yeah. We did this and we have to look for the galaxies in a different way. And now let's rerun the whole thing. And it's not low latency anymore. So what should we do next to explore what we can leverage from what we have?
Yes, so just a couple clarifications just for everyone. So everything that I talked about was very focused on kind of the low latency aspects of this stuff. The like this catalog that was produced a year after data taking. And so of course there is reprocessing and production of these catalogs that exactly needs this kind of resource. One thing that I would be excited about, or I want to explore, and I'm going to talk to some folks today, I hope about it. I would like to explore triggering some of these kind of offline, like Bayesian inference workflows through some of the web applications that we build, because astronomers, as I mentioned, they're all interacting through front ends, and but what happens is they pull the data down. Maybe then they open a Jupyter notebook and figure out how to run some Bayesian inference scheme. I think we should be able to trigger some of those very slow, computationally expensive, using GPUs or not type workflows directly from the web apps, authenticate through OSG to, distribute workflows and get data back. And so I think this is where, not just for kind of the ML workflows, but also just for the kind of the slow compute jobs, being able to bring that compute to, again, to folks in the front end, right? Because there's an entire generation of LIGO graduate students, who are vaguely comfortable with, logging into the OSG node in LIGO, triggering some kind of Condor job. But that's just some subset of them. I think enabling a lot of this through front ends is going to be, the way to get more people access to Rubin and LIGO and so on.
But there's the flip side of it. Let's assume that they are all happily doing it. Somebody has to bring in and manage the capacity in the back end.
Of course.
So the more success you have in bringing every kindergarten student to do gravitational wave, is that we have to figure out as a community, how do we manage whatever capacity we have to,
yes.
And I feel we need to put together a group that we start talking about it and taking steps, whether it's for testing. I have a new model, I want to try it out on all data, how good it is compared to your detection to convince you that it's, so there's a lot of offline, which is not, and I feel this is missing.
Yep. I think, yes, so there's a mix of technical challenge, but also sociological challenge there, because of course,
I will turn it, the sociological challenge, and then there's the technical one.
Right. So within LIGO already, we run 7 or 8 pipelines just in low latency, and it's even more, of course, in the offline. And so we have meaningful challenges actually just putting together agreeing to put together the data sets and actually do apples to apples type comparisons. And so there's the sociology to overcome there, in addition to can we actually then, once we agree on something, to actually, figure out how to trigger workflows on the OSG or whatever to actually measure, do I measure more binary black holes than you do, right? And so there's both, of course.
Yeah. All right, so Frank.
I had a question for regarding your open data. If you take the totality of all gravitational waves observed and published in peer-reviewed journals, how much of that comes from the open data versus the LIGO collaboration itself?
So okay. So I'm going to interpret the question and let me know if I interpret it properly. Okay, so indeed, the LIGO-Virgo collaboration, they take data, they run their analyses, we produce a catalog, and often we try to do that in time for the data being released. However, the LIGO, Virgo, Kagra folks are not the only folks who can go into that data stream and identify binary black hole mergers. There are groups at Syracuse and the Institute of Advanced Study in particular who run their own pipelines and have produced additional binary black hole candidates, for example, running over our data, producing let's say a handful more detections than these, kind of depending on where you want to set your false alarm rates. And so the vast majority is stuff that we publish, but there are catalogs out there adding that have been since at some level confirmed, or at least kind of their false alarm rates evaluated by LVK stuff, and they look pretty good. Did I answer your question?
So
Yeah.
let me play back what I
Yeah.
heard. So in essence, the vast majority of what is in the public domain as published scientific results comes from the LIGO collaboration, and the open data adds marginally to it.
Yes, I think so this is true for especially true for kind of the binary black hole compact binary coalescences. There are computational problems, things like looking for pulsars in gravitational wave data, which are orders of magnitude computationally more expensive than the stuff we're talking about here, where you're just looking for a specific spin period in particular, and then a spin down period. And so there are groups in Germany and elsewhere with the expertise and actually with the compute to directly compete. And the limits that they produce are sometimes better in certain parts of the parameter space than we do. So in this world, LBK is kind of dominant, but there are other science cases where, the slow stuff, right? The stuff I don't work on as much where, yeah, outside groups do compete very well.
Thank you.
All right, let's thank Michael again.